Alright guys, today we're going to talk about impedance, which is a new concept that we need to start talking about because we're going to have circuits that have both resistors and capacitors. When we were talking about resistors, we said that a resistor's job was to slow the flow of current. So if I had a battery and a resistor hooked up, then the resistor would limit the amount of current that flowed through the circuit, provided resistance to the flow of charge. A capacitor doesn't do exactly the same thing, but we can think of the capacitor as having a similar property because we said if I had a battery hooked up to a capacitor, then while it was charging, the initial flow of current would be very large and it would charge quickly. And as time went on and the capacitor charged and gained a potential difference across it, the flow of current would slow down. And so it would charge less quickly. So we could view this as the capacitor having an increase in resistance as it's allowed to charge. If I put a capacitor into a circuit with a function generator where the function generator is giving a signal that looks like this, and it's waving relatively quickly, then the capacitor is not going to have a whole lot of time to charge. And because it is not getting a whole lot of time to charge, the flow of current isn't going to be restricted by all that much. If instead, so this was high frequency. If instead the frequency was very slow, then the capacitor is going to get plenty of time to charge, and we're going to see that the capacitor has is able to develop sort of a resistance to the flow of current. So what's interesting is the resistor's resistance was always some value. It was always the same. And it was based on the material and the diameter of the material and the length of the material. But it didn't change based on the type of signal we were putting into the circuit. A capacitor's resistance or impedance does change. And so a capacitor has something called reactance. And reactance is this idea that we're talking about, the fact that the capacitor will resist a flow of current based on how quickly the signal or the voltage is changing. Resistors have resistance, and we've kind of taken that for granted thus far. The symbol for reactance is X, and the symbol for resistance we've been using is R. They both have the units ohms, so the units are not different, but the capacitor has a new symbol X for reactance. And the equation for the reactance is 1 over omega C. and that's the magnitude of the reactance. We talked about before that omega is the angular frequency, so if we wanted to put it in terms of frequency, it would be 2 pi Fc. That's the reactance of a capacitor. The resistance of a resistor is just its resistance, whatever it's listed as. So what's interesting is that a capacitor's resistance, its reactance, is frequency dependent. It depends on frequency. And because it's inversely proportional to frequency, if the frequency is high, the reactance is low. So if the frequency is very high, the reactance is low. And if the frequency is low, the reactance is high. We were talking about this earlier with capacitor charging. If the capacitor is connected to a DC signal, then it will charge up to some maximum voltage and very little current will flow. So if the frequency is 0 or DC, meaning it's not changing at all, then the capacitor has a very high reactance. It's going to limit the flow of current by quite a bit. And again, if the frequency is very high, then the reactance is low. So to put this together, we have a new word called impedance. And impedance is the combination of resistance and reactance. And the symbol for impedance is Z. And reactance and resistance don't really add together very well. And so impedance is actually a complex number. So we would write the resistance plus the reactance J, where J is actually the square root of -1. Electrical engineers don't like to use I for the imaginary number because I was already taken, so we use J. But it's still the imaginary number, the square root of -1. So the impedance of two things in series, of a resistor and a capacitor in series, would be expressed as a complex number, as is shown here. If I wanted the magnitude of the impedance, meaning I don't really care about how much of it is reactance and how much of it is resistance, I just want to know what's the magnitude of the impedance, then I would add it using Pythagorean's theorem. So I would have r squared plus x squared and then take the square root of that. The reason for this, and I'm not going to get too far into it, is actually impedance is something called a phasor, and one axis is real numbers and the other axis is imaginary numbers. So this is actually the imaginary number plane. And so if I have say a resistor with a resistance R and a capacitor with a reactance X, then the length of that line is given by Pythagorean's theorem, and the length of that line is the magnitude of the impedance. And that's all we're really going to say about that. If you're interested more in that, it's called phasors, and it's something that we talk more about in the next class. What I'd like for you guys to do is to be able to calculate the reactance of a capacitor the impedance of a circuit that has a resistor and a capacitor, and the magnitude of the impedance. So let me give you an example. Let's say that I have a circuit that I'm driving with a function generator whose voltage peak to peak is 5 volts and whose function or frequency is equal to 1 kilohertz. And let's say I have a capacitor and a resistor. If the capacitor is equal to 10 microfarads, then I can find the reactance of the capacitor by using the equation 1 over 2 pi frequency times capacitance. So in this case, the reactance would be 1 divided by 2 pi, the frequency in hertz, so 1000 hertz, and the capacitance in farads. Micro is 10 to the negative 6th, so I'm going to have 10 times 10 to the negative 6th farads. So we're going to type that into the calculator. We're going to want to make sure that we're really careful with parentheses while we're doing this. So I'm going to have 1 divided by the quantity 2 times pi times the frequency, which was 1000, times 10 times 10 to the negative 6th. And that's going to give me 50 over pi is my exact answer. We can just round it. And that's going to be about 15.9. And the units are still ohms. So that's my reactance. Let's say the resistor is 30 ohms. Then the impedance of this circuit, the total impedance of the circuit, would be the resistance plus the reactance times the imaginary number. And so in this case it would be 30 plus 15.9 J. That would be the total impedance of the circuit. The magnitude of the impedance of the circuit would be given by the square root of 30 squared plus 15.9 squared. Notice we didn't include J. That's left out. We just want the scalar, the number itself. So we'll have that. And we can use a calculator to determine what that is. So we'll have the square root of 30 squared plus 15.9 squared. And that's about 33.95 or 34 for rounding. Okay, and that's how we find the reactance of a capacitor, which was here, the impedance, the total impedance of the circuit, which was here, and the magnitude of the impedance of the circuit, which is there.